मम्मा को बस
Good afternoon, Professor.
Good afternoon. Hey, Tariq. I'm going to get started with the housekeeping because we have a lot to do today. The plan for today's session is I'm going to lecture for about an hour and 12 minutes until 3:15. And then at 3:15, you will do the labs with TAs, led by Sam. It's customary for the labs to be done by the TA, so we're going to do it in this virtual iteration as well. Yeah, I can extend the homework till Wednesday, but I've already, yeah, that's fine. I'm happy to give you another 48 hours for the homework. Let me just give you a few. You're welcome. Let me just give you. You're welcome. A few administrative piece of news. I've graded 60% of the midterm, and those marks are up. I just thought I would share them, even though the final mark is not there yet. Because I know some of you guys are anxious. The grades are very high. I will refrain from, I will refrain from interpreting the grades at this point. Yeah, I'm not going to interpret it other than say that you guys are doing well in the course. And so the TAs are going to grade the remaining 40%, and I just gave them the solution this weekend, so give them a little bit of time, but you have the grades for the multiple choice section as well as the first two problems. The final mark will be out of 100. So 25 for the multiple choice, 25 for each of the three problems that you did. Again, the average grade is like an order of 80%. It's high. So you guys did well. The other thing I wanted to say was that the YouTube channel has all the lectures up until last week. The Blackboard lecture slides with solutions are up for lecture 7. Homework number 5 has been posted and is not due until 2 weeks from today. I'm going to extend homework 4 till Wednesday at midnight, so give you another 48 hours. And we begin today lecture 8. I'm not going to waste any more time talking because we got, unfortunately, a lot of ground to cover. Let's see. I guess I'll do this. All right. So, I mean, we're not really behind. We're where we usually are at this point in the course. It's just that the curriculum is too ambitious, and there's just not enough. There's not enough time to cover everything that this course has, especially now with the labs starting. But that's okay. You're still gonna learn everything. You're just gonna have to do a few of the examples on your own time. So here today, I'm gonna give you a few minutes of theory, and then we're gonna do 5 problems. 2 of them are solved on the slides, and 3 of them I will solve with annotations. We're covering second order circuits. So here are 4 pictures of second order circuits. By definition, they have two storage elements, where a storage element is either an inductor or a capacitor, or two inductors or two capacitors, or one of each. And they cannot be reduced to a single storage element. So the reason that this material is called second order circuits is because when you write out the equations that describe the inductor current or the capacitor voltage, you obtain a second order differential equation. Now, nobody likes differential equations. However, the nice thing about this circuits course is that we don't do anything fancy in solving these equations. We assume a general form solution that has coefficients, and you plug in your initial conditions and you solve for the coefficients. You really do not have to know much about calculus to do well in this lecture on this material. We don't require you to do anything sophisticated. The only thing that you need to do is come up with two initial conditions, right? So for a first order circuit, you had to find the initial capacitor voltage or the initial inductor current. Now you also need to find the initial derivatives. Okay, so that part is the most challenging in these problems. And I'm gonna try to demystify it. It's doable. It's just logic, but definitely getting the initial values and the derivatives is the hardest part. And so the initial condition and the final condition are easy because generally those circuits become a lot simplified at time 0 and at time infinity. But the derivative at time 0 sometimes requires a bit of thinking and a bit of circuit analysis. And so that is what I'm going to try to focus my attention on. All right. So remember, we're either going to be solving for the capacitor voltage V or the inductor current I. Remember continuity. This is hugely useful because you can evaluate this circuit at time 0 minus and then propagate that capacitor voltage to time equals 0 plus. That helps you with those initial condition on the derivative. Same thing with the inductor current. You can solve for the inductor current before the switch happens and then still use that value right after the switch happens. And that helps you get those initial conditions that you need to solve the problem. Okay, everything else. This lecture is really about the problems. And in general, from now till the end of the course, there's a little bit more theory, but mostly it's just the art of solving circuits, applying the correct law in the right place with a little bit of math at the end. But, we're not introducing any radically new concepts at this stage. Okay, so here's problem 1 of 5. We have a circuit with a switch that goes from the closed position to the open position at time equals 0. We have an inductor here, we have a capacitor here. And we are asked to find 6 quantities. The inductor current after the switch, the capacitor voltage after the switch, their initial derivatives, and the final value of the inductor current and capacitor voltage. So in this example, I'm going to walk you through the textbook solution, and then I'll gradually ask for more and more of your help. So basically, the recipe here is to draw the circuit at 3 different time points. Time equals 0 minus, time equals 0 plus, and time equals to infinity. Okay, so you're drawing the circuit at 3 different time points. So first things first, let's draw the circuit when the switch is in the open position. Okay. Remember, at time equals 0 minus, the circuit is in steady state, which means that the inductor is a short and the capacitor is in open. That makes your life a lot easier, right? Because now you just have a very simple circuit that has a battery in series with two resistors, right? And so the current that is flowing in this loop is just equal to 12 volts divided by 4 plus 2, or 6 ohms. So there's 2 ohms flowing through the short-circuited inductor. And there's a voltage drop of 4 volts across this resistor because of Ohm's law. 2 ohms times 2 amps gives you 4 volts. That's the voltage that is parallel with the capacitor, right? So the initial value of the capacitor voltage is equal to the voltage drop across the 2 ohm resistor. Okay, so that's kind of the first insight, is to see that this capacitor, before the switch opens up, is in parallel with the 2 ohm resistor. Okay, so we have our initial conditions. So we're already 1/3 of the way there, right? Because we can apply continuity to get I at 0 plus and V at 0 plus. So we can check off this and this. And now we move on to step B, which is the hardest part. All right. So how do you get these initial derivatives? Well, basically what you do is you propagate those initial conditions on I and V forward by 1 instant in time. So now the switch, just show you, this switch is now open. And so this whole branch is gone from the circuit. And the inductor and the capacitor are not in steady state. They're now active. They're undergoing a transient. However, at that moment in time, T0 plus, they still obey continuity. And therefore, at the time instant, time equals 0 plus, the inductor current is still 2 amps. Okay. And we also know that, and this is the trick here. I mean, it's not really a trick, but it's just math. But we know that so at this time instant, both the inductor current and the capacitor current are still equal to 2 amps, right? Because the inductor obeys continuity, that's step 1, and the capacitor is in series with the inductor. So that's step 2. So both the capacitor and the inductor have a current of 2 amps at time equals 0 plus. And we also know that the derivative of the capacitor voltage multiplied by the capacitance is equal to the capacitor current. This is the first principles here, this equation. We know this, it's 2 amps. We know this, it's 0.1 farads. So we can solve for the derivative at time 0 plus simply by dividing the capacitor current by the capacitance. So 2 divided by 0.1. That gives us our initial derivative. So this is how quickly is the capacitor voltage increasing. And it's increasing at a rate of 20 volts per second. So with every second, the capacitor voltage increases by 20 volts. Okay. So now we have the initial condition on the capacitor current. We also need an initial condition on the derivative. So we have an initial condition on the derivative of the capacitor voltage, rather. And now we need an initial condition on the derivative of the inductor current. So we basically apply the same trick. Namely, we know that the voltage of an inductor is proportional to the derivative of its current. And we need this. So we need to figure out what V of L is. And we need to basically solve this equation for di over dt. So now let's apply KVL around this loop. We have a voltage rise of 12 plus a voltage drop of 4 times I0 plus. And remember that we know the value of I0 plus. Then we have a voltage drop of VL and a voltage drop of V. So it's easy to get the symbols mixed up in this section. So just pay very attention to the subscripts. We're always going to use V without any subscripts as the capacitor voltage. And we're always going to use I without a subscript as the inductor current. So this is the inductor voltage. This is what we're trying to solve for. But we know the value of I0 plus, and we know the value of V0 plus. And so now we just rearrange and we solve for V of L at time equals 0 plus. It must be equal to 0. And therefore, the initial derivative on the inductor current is also equal to 0. Because again, for an inductor, the slope of the current is proportional to the voltage. So the voltage is 0, the slope of the current must also be 0. I'm just going to stop here. And if anyone is confused as to how we got these initial conditions, you should speak up.
Professor, I'm confused. Can you repeat
Yeah.
that point of how we found the initial derivatives?
Yeah. So basically what you do is in this picture, we know the value of I, which is 2, and we know the value of V, which is 0. And so the capacitor, the derivative of V is probably easier to understand. So for a capacitor, the derivative of the voltage is equal to the current divided by the capacitance. That's our fundamental, that law applies at every time point, which means that if we can get the capacitor current, we can get the initial derivative. And so we have to figure out in this circuit, what is the value of the capacitor current? And notice that the capacitor is in series with the inductor. So if two elements are in series, they are guaranteed to have the same current. But we know that the current I here is 2. We got that from the continuity in the previous slide. And therefore the 2 amp inductor current also applies to the capacitor. And then you just plug in, so you basically, so for a capacitor, so when you solve, so basically the equation for a capacitor is that I is equal to C V prime. And you are interested in the V prime. So to solve for V prime at 0, you just divide I of 0 divided by C. So that's the technique, and this is a parentheses here. That's a technique for getting the initial derivative of the capacitor voltage. For a inductor, we have this equation. And so to get the value of I prime at 0, we have to get the initial value of the voltage of the inductor, V0, and divide it by L. Okay, and so what we did in these problems basically is solve for the inductor voltage, which goes in here, and the capacitor current, which goes in here. Okay, so that's the trick. In all these problems, to get the derivative of v, you gotta get I of c, and to get the derivative of I, you gotta get v of l, and that's what we're going to be doing in every problem. Okay, lastly, the last step is easy. You just redraw the circuit at time equals 0 prime. So at time equals 0 prime, there's no more current flow, right? Because there's not a complete path for the current to flow. And so the current through the inductor is 0, and the voltage across the capacitor is just equal to the battery. Oops, is just equal to the battery voltage, which is 12. All right, let's move. I'm gonna clear this, and I'm gonna do the next one because I'll be annotating it. Is gonna go much slower. All right. Yeah. Okay. So again, we're asked to solve for 6 quantities. The inductor current at time equals 0 plus, that's here. The capacitor voltage at time equals 0 plus, that's here. Then their initial derivatives and their final values. So the first and last steps are easy. The middle step is the one that requires usually some thinking, but it's doable. So I'm just gonna, I solved all of these. I like to solve these every year. I like to solve them before class just so that I have everything fresh in my mind. So the first thing we're gonna do is draw this circuit at time equals 0 minus. And you will see that the circuit is greatly simplified. Why? Because the capacitor is an open circuit and the inductor is a short circuit, right? So we're just gonna have the 2 ohm. Then we're gonna have the open circuited capacitor. Then we have the 10 ohm. Then we have the short circuited inductor. And we have the battery, which is 24 volts. And this is 10. And this is 2. And importantly, I is defined over here. And V is defined over here. So who can tell me the value of I in this picture? Okay, let's see. 2 amps. Excellent. Thank you, both of you, for providing the correct answer. It is 2 amps, right? 24 volts divided by 12 ohms. So 2 amps is the value of the inductor at time 0. Time equals 0 minus and 0 plus because of continuity. Okay. What about the value of V at time 0 minus? Four, excellent, right? Exactly, 2 amps times 2 ohms equals 4 volts. Okay. So now we have this one solved and this one solved, right? And now we got to move on to these two. Okay. So for this one, we're going to redraw the circuit at time equals 0 plus. Okay. So here is where we take this, evaluate the circuit after the switch, and we're going to carry forward these values. So let's draw the whole circuit. And this time, the capacitor is in there, but we know its voltage at that particular point in time. Its voltage is still going to be 4 volts. So I'm just going to write V is equal to 4 here. And this 10 ohms is going to be gone. It's going to be shorted by this, by the switch. And I'm going to do my best to draw the inductor here. And this current here, at this point in time, is still going to be 2. Okay. And so now, and this is 2 ohms, right? So we know that the voltage between the capacitor across the capacitor is 4, right? And we know that there's 2 amps going through the inductor. So here is actually, this really is like a kind of like a logic puzzle, right? So there's 2 amps going in here, and there's 4 volts across the capacitor. So who can figure out how much current is flowing through the 2 ohm resistor? So I'm going to try to lead you to the answer. There's 2 amps flowing here. Moreover, this resistor has a voltage across it of 4 volts, right? So we have an answer. I think someone's figured it out. 1 amp. And how did you get the 1 amp? Why not? So the voltage across the 2 ohm is 4 volts, and its resistance is 2. So how do you get a voltage of 4? Oops, sorry. Yeah, it's 2 amps. There you go. Yeah, the current here has to be 2 amps, right? Sorry, it's the toggling between the annotation and the chat and the PowerPoint is a little bit challenging for an old guy like me. So there's 2 amps flowing down through this 2 ohm resistor. There has to be, otherwise you would not get a voltage of 4 volts here, which means that how much current is flowing through the capacitor? Exactly, 0. Very well, very, very well done, right? So now we can write that IC at 0 plus is equal to V prime at 0 over C, which is equal to 0 amps per second. Or sorry, I screwed that up. So we have that V prime, and we know that this is equal to 0. Therefore, the derivative of the capacitor voltage is equal to 0 volts per second. What about the value of the inductor voltage at time 0? Oh, we have a question, I think. Why didn't add 10 ohm? Because the 10 ohm has been shorted by the switch. This switch, right? It short circuits the resistor out. So it's gone from the it magically disappears from the circuit. So what is the value of the inductor voltage at this? I've lost my cursor, so give me. Okay, so what is the value of the inductor voltage in this circuit? Right, this is a 20, oh, let's see if we got 20, excellent. Excellent work. That is exactly right, right? Because there's the voltage at this point here has to be 24 volts. And the voltage here is 4 volts. And so the difference between 24 and 4 is 20. Oops. Go back to annotation. So the derivative of IL, or just call it I prime at 0 plus, is equal to VL. Or let me just spell it out step by step. VL at 0 plus is equal to 24 minus 4 is equal to 20 volts. Therefore, the derivative at timing, and you'll have all these solutions posted. I have PDFs of all the solutions, so don't worry about writing anything down. So the derivative of the inductor current is equal to the voltage divided by the inductance. So it's equal to 20 divided by 0.4, which is equal to 50 amps per second. All right, so now we're done. We are done with the really hard stuff. Now we draw, oh, let me just, I'm gonna take your question. Go ahead and start with your question while I restore my cursor.
I don't understand. Can you explain how all the current goes through the two ohm resistor? Because I thought
Yeah.
I thought it was a 1 amp, so I wasn't sure.
Yeah, so in this picture, there's 2 amps coming out of the battery. Do you follow that?
Yeah.
Yeah. And so that 2 amps, we know that some of it's going to go down the resistor and some of it's going to go down the capacitor. We have to figure out how much. But we also know that at this time instant, the capacitor has a voltage of 4. We got that from continuity. And that capacitor is in parallel with the resistor. Right? So that voltage is shared between the resistor and the capacitor.
Oh, got it.
Okay, good.
Thank you.
No problem. Okay, so the last step is just to, the last step is easy. It's always the easiest step. The time it goes to infinity because everything's gone, usually a lot of things. So we have the resistor. Basically what we have is an open circuited capacitor. We have a short circuited inductor, and we have the battery. Right, and this is 2. So the question is, what's the value of I? And what's the value of V? Here. Okay, so I'll just solve it in the intro. Oh, we got an answer. I is 12, exactly. And what's the value of V? Okay, right, so I of infinity is equal to 24 volts over 2 ohms is equal to 12 amps. And V at infinity is just 24 volts, right? It's obvious that the capacitor in this picture is in parallel with the battery. So it has to have the same voltage. All right, we made it through our first, second order circuit. All right. Now I'm gonna kill Zoom by this time this lecture ends. All right, I think the next problem is a slide problem. Oh, we're gonna skip this one. I encourage you to do this one at home. Maybe when you're having a hard time sleeping. Okay. We are gonna do this one though. And actually I'm gonna do this one. I think it works better this way anyways. Yeah, okay. Time equals 0 minus. Okay. Looks like an emoji, it's not. Okay. That's it. Let's figure a way out of this issue. Okay. So let's redraw. We have to solve for the same thing as before, but now there's an extra part. There's the resistor here, VR. We have to solve for the voltage across this 5 ohm resistor in addition to the inductor current and the capacitor voltage. All righty, let's draw the circuit at time equals 0 minus. This thing is not in the circuit at time equals 0 minus because the step function U of t is off for negative time. So we don't have to worry about all this. So let's draw the circuit, right? So the capacitor is open circuited. Sorry, yes. And that's a really ugly resistor, I'm sorry. The inductor here is short circuited. And we have our 3 amp current source is pointing down. And we are asked to solve for 3 things. I of L, VR, and VC. Okay, and this is 5 ohms here. It's a simple circuit at this point, right? You just have a current source, a short, an open, and a resistor. So now, who can tell me that? Let's start with I of L. I think I of L is the easiest to obtain in this circuit. What is the value of I of L here?
3.
3 is a very good guess. Almost. It's -3, just because the polarity. That's excellent work. IL at 0 minus is equal to IL at 0 plus is equal to -3 amps. What about the value of VC at 0 minus? And here you have to justify your answer, because I think the answer is probably easier to get than explaining why. What's the explanation for why? I'm just going to say VC is equal to 0. The question is, how do we know that for sure? In this circuit.
We know that because there's no load in which the current is passing through.
Yes, almost. There's no, that's right. There's no, the answer is because all of this current, the current is going like this. And what's actually true is VC is equal to VR, believe it or not, in this picture, right? Because they have the same upper terminal and lower terminal. Because of this short, VC is equal to VR. And they're both equal to 0, like you said, because there's no current through the load. And that's equal to VR 0 plus. Okay. So we can check off this, this, and this. And now we have to move on to these, which is the least fun. All right. Time equals 0 plus. All right. Let's draw the circuit at time equals 0 plus. So now we have both current sources in the picture. We have the 2 amp current source. And remember, now the capacitor is active and it's undergoing a transient. We have the 5 ohm. I did a better job of drawing the resistor there. Let's see. Ooh. Oh, I'm a Picasso of circuits. Okay. All right. 3 amps. This is 2 amps. This is 5 ohms. And then this is VR. It's important to have the polarity straight here. This is VR. This is VC. And this is IL. And we know a few things, namely that that VC, because of continuity, VC is equal to 0. So this point here is sitting at 0 volts. And IL is equal to -3. I'm gonna try to scribble on top of it. A mess. Okay, so this point here is grounded. So if we draw the ground over here, this point is grounded as well, because VC has to be equal to 0 volts. Okay. So in this picture, which is admittedly a little bit messy, we're gonna need to know how much current is flowing through the capacitor. Remember, that's our trick for getting the initial value of the derivative of the capacitor voltage. So in this picture, my question to you is, how much current is flowing through the capacitor? So what is the value of IC, capacitor current, in this picture? If you had to guess, just by looking at it, if you had to guess, what would you say? Oh, we have 3 answers. Okay, Christian, you got the correct answer. It is 2. But again, I applaud you guys for trying, because this is definitely a challenging problem here, right? So the answer is 2 amps, and the reason is, let's think about the 2 sources. So the way I reason this is, this 3 amps is all going here. So the 3 amps does not make it beyond this mesh, right? Because we know that there's 3 amps down here, 3 amps this way, and 3 amps up here. So we know that all of the 3 amps is contained to this mesh. Similarly, we know that there's no current over here because VR is equal to 0 volts. Because again, we determine it here. And so this 2 amps will, similarly be contained to this left mesh, right? Although if any of this 2 amps reach the resistor, there would be a non-zero voltage, but there isn't. It's equal to 0. And therefore this 2 amps has to all flow in the left mesh. And so at this time instant, nothing is happening in this middle resistor. Okay, so now we can say that let me see if I can, IC is equal to 2 amps, which means that the derivative of V is equal to 2 amps over 1/5 is equal to 10 volts per second. So that's the initial condition on the derivative of the capacitor voltage. Again, admittedly, this problem does require a lot of thought. So again, I encourage you guys to sit with this and just convince yourselves that this 2 amps will not, all of this 2 amps will go down the capacitor. And all of this 3 amps will go up the inductor, and nothing's happening in the middle. Okay, let's talk about the inductor voltage. We know that we need a value of the inductor voltage at 0 plus, right? And so notice in this picture that because this 5 ohm resistor in the middle is dead, the inductor voltage has to equal the capacitor voltage, which is equal to 0. So we know that the inductor voltage has to also be equal to 0. And therefore, the initial derivative of the inductor current is equal to 0 amps per second, right? So at this time instant, 0 plus, the inductor and the capacitor are in parallel. Why? Because there's nothing happening here. And so you can ignore this resistor. Okay, and the last part of this is just that simply for the reasons that I've just said, because between at time equals 0 minus, there was nothing happening at this resistor. At time equals 0 plus, there's nothing happening at this resistor. And therefore we know that the derivative of V of R at 0 plus is also equal to 0 volts per second, because the instantaneous change, the change from 0 minus to 0 plus is nothing, because nothing changed from this point to this point at the resistor. All right, the last step is the easiest. Time equals to infinity, because a lot of the circuit drops out, right? So the 2 current sources are actually both still here, but the intervening circuit is very minimal, right? We have an open circuited capacitor. We do have the resistor. And this is, sorry. So this is 3 amps. And this is 2 amps. And this is 5 ohms. So my question to you is, first of all, what's happening in this circuit? We know, for example, that current will tend to, well, actually, I'm not even going to say that because they can confuse you. But let me just, because we're kind of running out of time, I'm just going to kind of lead you to it. This is still going to be, this is all going to be 2 amps because of it's in series. And so you can ignore this open circuit for now. All of this 2 amps is going to go through the 5 ohm resistor, right? So that we know that the 5 ohm resistor carries a value of 2 amps from left to right. We also know that this 3 amps is coming out over here. So this here is 3 amps. Therefore, what is happening over here? What is the value of this current? Okay, we have an audience answer, 2 of them. -1, excellent. Both Jonathan and Omar, that's excellent. It is equal to -1, right? I of L at time infinity has to be equal to -1 amp. What about the capacitor voltage in this picture? What is the value of the voltage between this open circuit? Keeping in mind that it has to be equal to the resistor voltage, right? Because we said that they're in parallel. This connection is shared, and this connection is shared. So what is their voltage? Two and a half. Almost. You divide it, but you have to multiply. So it's 2 times 5, not 2 divided by 5. Yeah, 10. Thank you. It's 10. Finish it up here. So it's equal to 10. 10 volts. Okay. So yeah. All right. So we're gonna move on. I'm gonna regain my cursor and clear all this. And why do we ignore the 2 amps at time equals 0 minus? Oh, no, it's, yeah. So the question is, why do we ignore the 2 amp source at time equals 0 minus, but not at infinity? So the reason, it actually has nothing to do with the capacitor. It has to do with this step function. So the step function is off for negative times, and it's on for positive times. So once it comes on, it stays on, right? So this is a step function. It's off, and then it's on, and then it stays on forever. So even though the capacitor becomes an open circuit, the current keeps flowing. It's just now at time equals to infinity, it goes like this, basically. Hopefully that makes sense. Okay, good. All righty. We have about 20 minutes and we've done 3 of the problems. So let's see if we can get through. All right, so now we're going. We just did this one. So now a little bit of theory just to give you guys a break from the puzzles. So we have our first second order, like canonical second order circuit. And it's the source free series RLC. So series RLC is very clear. I mean, you have a resistor in series with an inductor, in series with a capacitor. This is like a classical piece of physics and engineering literature, right? This circuit. It's common. It has a lot of interesting properties, and we're going to study it from a circuits point of view here. Source free just means that there was a battery or a current source connected, and then we disconnected at time 0. and then that energy dissipates. And we're studying the time course of that dissipation. Okay, so again, this is useful for filtering and for telecommunications. And we know that initially there's some energy that's contained either in the capacitor, in the electric field that is stored in the capacitor, or in the magnetic field that's stored in the inductor. Okay, we're going to call those initial voltages V naught and I naught. Okay, so again, these are just our initial conditions, which we will need to solve for in many cases. But here we're just going to give them, we're going to attribute their values by constants. To constants. Okay, so we have V naught and I naught, and those are the initial values of the capacitor voltage and the inductor current. So now let's apply KVL in this circuit, and we're going to assume a common current of I, right? Because this is a series circuit with a single mesh. We have 3 voltage drops. We have a voltage drop of Ri across the resistor. We have a voltage drop of L times the derivative of I across the inductor, right? Because the voltage across an inductor is equal to L times I prime. And we have a voltage drop of 1 over C times the integral of I, right? Remember that the voltage, to get the voltage drop across a capacitor, you integrate the current. And so that's equal to 0. So now let's take the derivative of both sides of this equation. And if you do that and just divide everything by L and then R, I believe, you get the following second order differential equation. So you get the second derivative of I plus R over L times the first derivative of I plus I over LC is equal to 0. And the way that you should think about this equation, you should think of it as a quadratic. So you should think of the derivative as a variable. And when you square it, you get the second derivative. And then, so this is the degree 0, degree 1, and degree 2. And that's how we're actually going to solve this equation. So if we solve this equation for I of t, then we have the solution to the current in this circuit. And we got this equation just by applying KVL. So from absolute first principles. Okay. So again, hopefully everybody is clear on how we derived this equation. It's just KVL with a little bit of manipulation. And so now our job is to find the times a function I of t that obeys this equation. Okay, so the way we do that is we're going, again, I said we're not going to do any heavy calculus in this course. We're going to assume that our solution has a general form. So if you may remember, there's a well-known result that states that the solution to a second order ordinary differential equation can be written as a sum of two weighted basis functions. F1 and F2 are the two basis functions, and those are generally going to be either exponentials or sinusoids, or a mix of the two. And A1 and A2 are the coefficients. So we're going to assume that there is a solution of this form to this equation. And then we're going to use our initial conditions on I and I prime to solve for A1 and A2. And that's it. You don't have to do anything sophisticated here to solve this second order differential equation. So for example, we already know we're going to have an initial value of I naught. And we can get easily from KVL an expression for the initial condition of the derivative, right? So let's write the KVL around this loop, but replace replace the capacitor voltage with a constant whose value is V naught. So this is the KVL equation at time 0. You can rearrange this KVL equation at time 0 for di over dt. And so what this equation is really saying is that if you have an initial value of the current and an initial value of the capacitor voltage, you can calculate the initial value of the current derivative. This is very useful because you don't have to worry about the kinds of things that we did in the previous problems, right? All you need is an initial inductor current and an initial capacitor voltage. And from that, you can calculate the initial derivative of the current. So students will ask me, do we need to memorize this equation? And, you know, I think that the best way to answer this is that if you're not comfortable with being able to write this equation out from scratch, you know, from first principles, then yes, you should memorize this. That for a series RLC circuit, you have, this is the expression for the initial derivative. Okay, but otherwise, if you can also just write the KVL equation at time 0 and solve and derive this yourself, but it's up to you. If you want to memorize it, you can. So now we have one initial condition and the second initial condition. And with those, we can plug. So we can plug those initial conditions into, we can differentiate this function, plug in the value of the initial derivative, and solve for A1 and A2. So, and again, this will all make sense when we do a few of these problems. For now, I'm just going to go back to what I said earlier, is that second order ODE can be thought of as a quadratic equation. So this is called a characteristic polynomial. Okay, so, and it has roots. And those roots can either be real and negative, both equal to each other and real, or both complex, right? So in our equation, the value of alpha, so 2 alpha is what's known as the coefficient B in the quadratic equation, right? So alpha is always going to be positive because resistance can only be positive and inductance can only be positive. Omega naught, which is the C in the quadratic. So if you have the quadratic equation, which I'll just write out here, you have ax squared plus bx plus c is equal to 0, right? We know that the roots of this equation are given by negative b plus minus square root of b squared minus 4ac over 2a. In this case, the a is equal to 1, the b is equal to 2 alpha, and the c is equal to omega naught. And both the alpha and the omega naught are themselves related to the circuit components. So namely, alpha is equal to resistance over 2 times the inductance, and omega naught is equal to 1 over the square root of L times C. Okay, so the important thing to note here is that the values of the R, L, and the C are going to tell you whether you have, just a little bit of text here, the values of R, L, and C are going to tell you whether or not you have 2 roots that are negative and real, right? So when alpha is bigger than omega naught, in other words, in this, just show you, right? So when what's in this square root is positive, in other words, when alpha is bigger than omega naught, then we have 2 real solutions, and those will always be negative. So if you ever are doing a problem and you get roots of your polynomial that are positive, you know you've done something wrong. The roots have to be negative because just by virtue of RL and C needing to be positive. Okay, so you either have two real negative roots, in which case our solution takes the form of a sum of two complex or two decaying exponentials. So S1 and S2 are going to be negative in this case. Obviously, the current, if S1 and S2 are positive, then the current would go to infinity if it was bigger than 1, right? So S1 and S2 are always going to be negative in this case. The second case is a special case. It's when alpha is equal to omega. When alpha equals to omega, we only have one real root. And so there, you know, there's a trick from in differential equations that if you only have one solution, you can get a second one by multiplying the first one by a linear term. And so this becomes the general equation for the case when alpha is equal to omega. And finally, we have the third case when alpha is less than omega. And in that case, what's inside this square root becomes negative, and your roots become complex, right? And so in this case, the general form takes the form of a synthesis of a decaying exponential multiplied by a sinusoid. And this brings me to another common question, which is, do I have to memorize these? And I'm afraid that in this case, the answer is unequivocally yes. You do kind of need to memorize these. The good news is that we're gonna do a lot of problems in this lecture, and you're gonna have homework problems, and so you'll have plenty of opportunity to practice these RLC circuits, and then it will simply, like, they'll be committed to memory without you even explicitly trying to memorize them. And so remember that you can always go back. You can always, from KVL, you can derive the characteristic polynomial. But many students just tend to memorize the value of the alpha and the value of the omega naught, and then they get their roots. And from the roots, you have to know which form of the solution you need to use. Okay, so I'm just going to talk for a few more minutes before handing it over to Sam. What I'm going to say about these is these three cases where you have two real negative roots, you have one real root, or you have two complex roots. The big difference between them is when the roots are complex, your solution has an oscillatory component. If your roots are both negative and real, there's no oscillation. And so your current starts out at some value and decays down to 0. But there's no ringing around that decay. Whereas in the underdamped case, so these three cases are called overdamped, critically damped, and underdamped. And so by looking at the picture, you can always tell if it's underdamped. So this is the case where you have complex roots. So if there's an oscillation, you know it's underdamped. These two are hard to tell apart. In theory, this one takes the longest to decay. And so if you're looking, because this is at the boundary between being overdamped and underdamped. And so if you're looking for something that has a long decay, you want the critically damped case. If you want something with a fast decay, you want the overdamped case. And if you want something with an oscillation, so a ringing, so like phones used to ring when phones were analog. That was a tone, that was a sinusoid. Then if you wanted ringing, you would take the underdamped. Then you would design your R, L, and C components to fit into whatever category you want. All right, some notes here. So just really some nomenclature. Omega naught is called the undamped frequency. Omega D, which is just the inverse of omega, is, you know, omega D, if you missed it, is just when alpha is less than omega, then what's inside the square root is negative. And so omega D is just the positive root there. You don't have to memorize these terms. You have to memorize the general form of the solution, but I will not be asking you about the, you know, the names of these alpha and omegas or their units or anything like that. What is important is that in the series RLC circuit, we solve for the inductor current. And we continue until we have a solution. And once we have a solution, we can use it to get a solution for the other elements in the circuit, such as the resistor voltage. All right, there is one special case, and that is when the resistance is equal to 0. So that's an LC circuit. So an LC circuit is special in that it never decays, because, and the math for that is here. If the R is equal to 0, then your alpha is equal to 0. And the alpha is what contributes the exponential decay. And if alpha is equal to 0, then all you have is a sinusoid. So that sinusoid will ring on forever. And what that basically means physically is that your circuit will oscillate. And so the energy will get transferred back between the inductor and the capacitor, and it will go on infinitely. So an LC circuit is a circuit where the initial energy gets transferred from the inductor to the capacitor, then from the capacitor to the inductor, and then that process continues. And so the inductor current will just oscillate forever. And we're actually going to do an example of an LC circuit. And the last thing that I'm going to say, mercifully, is that it's difficult to tell which of the three cases, overdamped, critically damped, and underdamped, you're in. Other than the underdamped case has oscillations. So if you see oscillations, you know you're overdamped. All right, we're not going to do these examples anyways. I'm going to stop talking, and I'm going to make Sam, oh, we have a question. I didn't see it until now. Mohiko, go ahead with your
never
question.
mind. I had my hand up from before.
Oh, okay, that's okay. That's good. So what Sam is gonna lead the lab, and he's more than capable of doing it. For the lab, this is a unique year because it's remote learning. We're not able to be with you guys when you're doing the lab. So we're gonna try to make the most out of it. The most important thing is that you get your hands dirty and you try to, you know, you try to make basic measurements. Sam's gonna walk you through it. I'm gonna make you the host, Sam, because I'm going to leave. What else did I want to say? Okay, hopefully all of you are here. I know that there's one student, at least one student doesn't have the circuit kit. That's okay. What, you know, we understand that a lot of you guys are abroad. That's not a concern. Sam, you will have until 2:45 to lead this. And just use it. And this first session is going to be an introduction.
2:45, you mean 4:45?
4:45, yeah. 4:45 is the official time of the Monday lecture.
Okay, I will try to end it early. Don't worry about it.
Okay. All right. Have fun. And I'll be back on Wednesday.
Okay. Thank you very much.
Enjoy.
So good afternoon. This is my very first time giving a lecture. So I knew some of you guys from when you visit my office hours. So hopefully you will have fun. So for me, when we are doing the Zoom lab lecture, just unmute yourself and ask me if you have any question, and feel free to interrupt me doing that. And also, I think if you check Blackboard, there's already a manual, a lab manual, the Google Doc version of it. The link to it posted on Blackboard, so please take a look and please open it and take a look if you haven't. So the idea is like for our today lab module, I like the guy is to give okay. The main object, the two main objective for today lab session. The first one is to walk you through the breadboard as well as the basic component that you will need to use for this lab and the next one, and then how to power the circuit and how to use it with the software, as well as one basic circuit. And for the for the homework, for the take home assignment, you would do some of the exercise such as identify the component, as well as to make a simple, a more advanced version of the simple circuit that we went through in class. So yeah, let's get started. And this is my first time doing something this, so I will try to do this. I'm using my phone as a camera and I'm talking on my laptop. So if there's any connection error, that's probably because of the multiple shot software that I'm using. And so yeah, according to the lab manual, we I think it's freeze again. I knew it. One moment. Yeah, it's working so again, and the Wi-Fi connection is bad. But yeah, let me hold it like this. This is easier this way. Come on, computer. What? Yeah. Okay. I hope it works. Yeah, the connection is bad. So we have the breadboard like this, and like the lab manual. And one of the main thing that you have to know is like for the black line like this over here, they are all connected. So if you put the one wire over here and one wire like this, they will be like connected, like they are connected. And then for the horizontal line over here on the top and on the bottom of the breadboard, like we mainly use it to ground and to power the circuit. So like over here, what I'm doing is I'm connecting two of the wire to one of the waveform generator for the advanced circuit that you guys may use. And this one will like the connection is horizontal. That means the entire for each of the entire row like this, they are connected in series, the two line. And for the breadboard, for each of the horizontal column, they are connected. So that means, for example, if we are looking at this particular component over here, what it means is I am like, let's walk through the circuit. So from this, like we have the positive power supply go to this wire over here. So this component and this component are connected, and then the wire. Yes.
Your camera's super up close and it's lagging a lot.
Okay.
I don't know if you
Would
can
it be-
show it on the picture from the lab manual.
Yeah.
Okay. Yeah. Okay. That's better. Give me one moment. Let me do my screen sharing. One moment. Share screen. Yeah, like the Wi-Fi. Oh, I think I know why. So one moment. There's so many moving components, and I don't know which screen you guys seeing. Which screen are you guys seeing? Let me check.
The manual.
You can see the manuals.
Oh, the manual. Okay. Yeah, I have. And fair. We try to keep it. So yeah, but like I don't have the circuit on like handy, but I think I can do it on this image over here. Yeah, that will work. Yeah, that will work. So what I would do. So yeah, like if you I need to do one more thing, and I will do the annotation. So yeah, like for example, like in the circuit that I just showed you, we have two components over here. This is the plus and this is the minus. So the entire circuit is like the entire row is connected for these two row, and then for this next couple of row, they are connected vertically. That means each of the column are one, like you can see it as one single node. So for a simple circuit that look like this, and I don't remember, but let's do this. So for a simple circuit that look like this, what we would do is the circuit component, the positive side of the battery will go in one moment, it's too small. 1, 2, 2. This will connect like this. And we have another wire that's go, for example, to this. And one wire go to this, and we will have and the resistor will go like this, and yeah, and then from this will go into this connection. Yeah, like I will show you like a picture like in a moment, but like I hope you get the idea. So the entire row over here is one single node, and like the first two row and the next couple of row, each of the like these are very important because like some student, some of my friends back when they were working with breadboard in my year, they had a lot of trouble understanding it. So I'm trying to explain this the basic idea. But yeah, if you get that, everything else is a cakewalk. And let me clear my drawing, and I don't know how to stop doing this. So yes, any question regarding the breadboard?
Yeah, I'm confused, Sam. So basically, the two lines on the top are connected in parallel, and the black lines are connected in series.
Yeah, no. Like the idea is they are all one single node. If you think about this, let me do the drawings again. And this time I will use this image. So this is your breadboard. And you can see it at this guy, this thing as one single node, like for example, we have one. So this is your breadboard, right?
Yes.
Where we have something like this. Yeah, they are exactly like they're looking, they are all connected. So regardless of how many components that you are connecting to this, they are all share a single connection. So like for the simple circuit that I just show you. So this is the power source, this is the resistor, and like if you can see, so like to demonstrate that this circuit, this is how we will connect the circuit, like this circuit to the breadboard. So the positive side of the power supply will connect to the red wire over here. And they will like this one will be in series with the entire row over here. So any of the connection branches out from this horizontal second line will connect in, we share the connection with the power supply. So for example, to expand this circuit, what we can do is we have another resistor that is in parallel with the power supply. So what it will happen is we will have the connection that go like this, and we have the resistor that go into this line, and we will go connect to this. And then for the like this one will be R1. This one will be R1, and then we have R2 over here. And the R2 will similarly be like this. We have connection that's drained from like the positive line that connect to the power supply over here. And we have the resistor coming
Okay.
to this, and then it's come back to ground. So this is how like your circuit will look like. Like, yeah,
Okay, this is connected in series.
they are all connected in parallel.
In parallel. Okay.
Yeah, so if you want a series connection, this is how it will look like. One moment. Oop. Oh shit. Boy, this is bad. One moment. How do I move this thing down? Okay, there you are. So to connect a series circuit, this is how it will look like. So to a series circuit. So wait, where's the eraser? Where's the drawing? So for example, if you want to have a serial circuit, this, oops, come on, move. This one will be R1, and this one will be R2. So to them to do this circuit, like, because like if you look at this image over here, they all share, like these two resistors share the same node with the power supply, so they cannot be in series. They are in parallel. They're in parallel. And if you want to do a serial circuit, this is what you will do. So based on this connection, like this is exactly like the drawing, if you like can understand it. So we have the connection go from this to this, and then it will go down to this resistor, and we have the resistor coming over here, and we connect to another resistor, and it's coming out like this, and this will go back out into the ground. So yeah, this is how you would connect. Got it?
Makes sense.
Like, I think you
Thank you,
will be able to play with that using an LED and a resistor in a moment, and you will see.
Okay. And the power supply is basically the box on top, right?
Yeah.
Okay.
Like I will show you the power supply in a moment. Clear my drawing, and I will close this. Any more question? I will take it as a no, and we will move on to a more difficult part of this today lecture. So the story of this is Tariq gave us an idea to provide you guys with a resistor value for each of the for each different type of resistor that you guys receive in the packet, but since we are too lazy to do individual labeling, so you guys will have to do it yourself. And I will show you how to read the resistance value of your resistor. So for all of your resistance, my connection is bad. This app is trash, and I would use it later. So like I will show you the component, and I guess I will have to show my face, and it's not desirable. One moment. Okay, does it work? And I hope you can see it. Yes. And I should show it the other face. Okay, one moment. I will. Yeah, I think you guys can see my face now, right?
Yeah, we can see your.
Okay. Actually, I just saw. No problem. So, like these are the resistor. We have, like, you guys have a lot of different type of resistor, like that come in a packet that look like this. And the idea of how to read the like a resist the value of each of the resistor is that you will identify the color of the band on your resistor and look at the chart to do the calculation. So for example, so if you scroll down to the lab manual, we have the I wrote out a guide to do how to read the resistance, the value of the resistor. But like to do it, I will do an example. So like if you look at this thing, I am not sure if this is clear enough. 1 second. Oh, this is bad. This is dark, but I hope you can see it. Like my light is a little bit low. So the one that we are going to work together is the resistor with a blue, gray, orange, and gold band. So if you guys if you want to take it out, you're more than welcome to. And don't worry too much about like which direction to read it, to read the resistor from, because the from most of the resistor, the last band, like in the correct direction, the last band will always have either the gold or the silver color. So you will read from left to right, and the last band should always be the red, the gold, or the should always has the gold or silver color, and then you will start reading from the leftmost band. So for example, the one I just showed you, the color is gray, blue, gray, red, and gold. Blue, gray. The one I show you is, oh yeah, I showed the wrong one. 1 moment. Should be, yes, this one. Sorry. Blue, gray, red, and yellow, which is the first example in the table. So if you look at the table, the blue is like the very first band, the color is blue. So if you look at the table, the value is 6, the first significant figure is 6. And then for the gray value, like the set, like because this is the second significant figure, we will actually let me do this. Yeah, blue, even though it's brown color, blue, gray, red, and gold. So blue, according to this table, is 6, and then gray is 8, and red, that means you time the entire value by 100, and the gold column means like I think it's the 5% tolerance, so you don't have to worry about the last band. So that means the value of the resistor is 6,800 ohm, or 6.8 kilo ohm. And another very common resistor value, I will do it again to demonstrate to you guys, is the 10K ohm resistor, which is this guy over here. So the color of this guy is really dark. So yes, but the color of this guy is like brown. We have brown color, and then black, and then orange, and gold. That means the gold color, like, because according to this table, brown is 1, black is 0, and orange means you time it by 1000. And 5% tolerant, that means this one is 10,000 ohms, or 10K. Any question? A lot of question, I hope. No, it's
I'm
clear.
lost.
Okay. Wait, what?
I'm confused.
Okay. What question do you have?
So yes, I'll tell you. So let's talk about the blue, gray, red, and yellow. How do
Okay.
you know which band to start from?
Oh, so the band from start from is like if you like, either you can the band from start from is you start from the leftmost band, which is blue. And how do you orientate it? That, like, remember I just said the gold and the silver band are always the last band. Like most of them will always be the last band. So you will leave them at the very end of your resistor. So it should stay on your right hand. And then like you will start to read from whatever on the left side.
Okay.
Yeah. So if you turn it around, you will not be able to read it. So oops. Yeah, the connection is off. One moment. Yeah, got it. So that means we cannot read from gold because there is no significant figure for gold and silver over here. So that means we will start to read from the other direction, which is blue, gray, red, not gold, red, gray, blue. Got it?
Got it. Thank you.
Okay, and like for the homework, you guys will do the you will read the color band of the remaining resistor that are in your circuit kit, and hopefully you can do it. If you have any question, just let us know and we will try to answer that or explain that to you.
So what does the silver and the gold band do?
The silver and the gold band, you mostly use it like if your circuit is very sensitive to tolerance, because like when you manufacture like the resistor, you cannot always get it to like 100% at 10,000 ohm exactly. So there will be some fluctuation in the real value of the resistor, and the gold and the silver band is like the quality control of it. So like for the gold, the fluctuation that by 5%, that means like your resistance value might vary from 9,950 ohm to 10,000. I hope my calculation is correct. To 10,000 10,050 ohm. That's why like when you do the op-amp circuit, even though the two resistor in your op-amp is like when you do the ratio between the two resistors are exactly one, but when you do the actual measurement between the input voltage and the output voltage, they will not be exactly one because of the fluctuation in your resistance. In the value of the resistor. Yeah. Got it? And any more question?
So what's inside this little resistance tube that's causing the resistance? Is
I
it
have
just a
no
different
idea. I
material?
have no idea. Don't ask me. Like this one is very simple because like these kind of resistors are very simple to like for you guys to play with, but like in reality, most of the resistance are extremely small. Actually, let me show you this. This one is for like what is it called? The circuit tinkering and the prototyping purposes. Let me see. Actual resistor in like in your like actually they use a lot of resistor in like whatever daily component that you got. Let me see if they have it. Nope, they don't have this thing on board. What's the term? I forgot. So not this thing. Yeah, this thing. Oh, surface mount resistor. Yeah, like that's the correct term. I haven't used this term in like a long. So for this thing is they are extremely small and like this thing are more like precise. but like they are very, very hard to do prototyping with these resistor. That's why like we are still using the very like big and like difficult to work with resistor, but they allow us to do a very quick prototyping of the circuit to see like if we have any issue in like when we design the circuit. Any question? And these things are very difficult to like without proper instrument. It's kind of difficult to like install this thing on a on the PCB. So if you do like Google some YouTube, that will like on the some video on YouTube that will show you how to like mount this resistor onto a PCB. Basically, there's like a piece and you will mount it into the pin and then very, very carefully put the resistor on the two pin, and they are in liquid form so they can wobbling around, and you will put the resistor like the circuit board into an oven, and it will start to melt the solder paste, and it will like fix the resistor in place. Yeah, like there's a lot of video on YouTube. You guys can look it up. It's pretty cool, I would say. And any more question?
What did you say was our homework?
It's in the lab manual. Like you will like go through go through your circuit kit and look for the resistor, look at the color band and calculate the resistance value of those resistors over here.
Okay, thank you.
Yeah. This should like if I did not make any mistake, this should have enough column for the number of components for different type of resistor in the circuit kit. So yeah, just do it. And the capacitor, the value is printed directly on the component, but they are extremely small and we are not going to use it for the next two lab lectures. So I will do it later and I will update the guide later for you guys. The next component is the LED. Yeah, the LED is a light emitting diode. That means they only allow current flow through one direction and not the opposite way. That's why, like, if you look at the LED on your circuit kit, they will have two pins. One is shorter than the other, and that means like the okay, one left. So that means one like the longer leg will connect to the positive side of your power supply, and the shorter leg will connect to the negative side of your power supply. And actually, one moment. Hopefully, I can show it to you guys. So that's the idea. And you will see that in the circuit that we are going through in a moment. Any more questions regarding the LED? Is the clear crystal in the circuit kit if you wonder. And don't try to power this thing with our resistor, or you will risk frying the resistor and you will need extra one, a new one. Because like this resistor have like current rating of very small, so yeah. Good.
Hi, so how do we find tolerance percent by looking at the table? Can you explain, please?
Pardon me, can you like speak a little bit louder,
Yeah,
please?
so how do we find tolerance for the resistors?
Oh, the tolerance, you don't have to worry about that, but it's the very last band, like it's the very last band in your one moment. It's the very last band in your resistance. like in your resistor. So they should either have the gold or the silver color over here. And like the tolerance is 5 joules, and like they will do the multiplication over here by the percentage. There's an example, and actually you can use this. Like for example, if you have the gold, like the gold color band at the gold color band as your last band, then the the tolerance should be about 5%. And if none, then yeah, it's about 20%. Like I barely use it, so that's the idea. And like we mostly pay attention to like all the band except the last one.
So we always look for the color like gold or silver or none.
Yeah.
Okay.
Yeah, like we will put this band as the last band, and we will start on the right hand side, and like we will start reading from the left hand side.
So we will fill out the table based on how many equipments we have in the packet, and just that will be the first assignment, right?
Yeah.
Okay.
Like I already have like did the first one for you guys, and we actually just did that in class. Like the gold tolerance. Actually, all of these are gold colors, so it's just 5%. I'm just leave that there for fun, for free extra credits for you guys if you want to see it that way. So yeah, you can just copy and paste if I remember correctly. Okay. Yeah, all of them should have the gold like
Yeah, all of them have the gold.
yeah, so all of them 5%, just fit in for fun.
I'm actually confused about like how do we calculate the resistor value, the ohms using the color?
After you finish this assignment, do you want me to go through these examples again?
Yes.
Okay, that will be easier, so I don't have to show the resistance. So one moment. So the color is blue, right? Gray. And red and gold. So the order of the color is very important. That means for the blue, when you look at this table over here, the value is 6. Just fill in 6. The gray, and this is the second position. That means the value is 8. And then the red color, if you look at the red, that means the multiplication, and by that is 100, 5%, and together you got 6,800 or 6,800. Got it?
Oh, okay. Thank you so much.
Yep.
Got it.
Any more question?
Yeah, so why did we look at the multiply column for red? Not
Because it's in the third position, and we since like we don't have the third significant value, we will use this guy as the multiplication.
say that again. Sorry, I couldn't hear you.
Yeah, like if you like the next to last band, like if you look at one moment, let me do like hex just this. Like we have 3 significant like we have 4, and one of them is the tolerant. And since we already got the 68, but like we don't have the multiplication, we don't know if it's 68 ohm, 6.8 ohm, or 6.8 k ohm, or 68 k ohm. So this this multiplication band will tell us what the exact value of that one. We don't know which is which, and using this one, which will tell us.
Oh, okay. So it should always be at the third color of the band, right?
Yeah.
Okay. Makes sense. Thank you.
Yeah, for the resistor in your kit, like that should always be the case, so you don't have to worry about the other case. Any more question? Okay, I will take it as a no, and feel free to, maybe you guys just don't know what to ask, so that's totally fine. Just let me know
I
if
have
you.
a question.
Okay, go on.
In the chart that you gave us to fill out,
Hmm?
the last column on the right side,
Hmm?
where are we getting the number component?
Just count it. Just count it.
Oh, the number of those specific ones here, give it to us? Okay.
Yeah.
Okay.
Like for example, the 2.8, for the 2.8, we have 2 in the kit, and I have 2 the same as you guys, so it's just 2. Just like just to make sure that you guys are not copying the result from anyone else. Yeah. Good.
What if someone was colorblind?
That's a really good question. I don't know actually.
Are they just screwed? They can't be electrical engineers?
Technically, actually, I think there should be an app for you guys to help you with that, I would say. There's an online calculator. If you do the Google search, it's an online calculator for how to read the color band of the resistor. And so technically there should be an app, and if there's not, you guys should work on it. It can be yeah, that will be really helpful. Yeah, I don't know the answer if you are colorblind. So if you are colorblind, let us know, and we will try to help you with that. Good. We have about 45 minutes, and so let's go through how to power this circuit. Oh boy, I have to untouch it. Fine. Bingo, that's good. So there are 3 ways to power your circuit. The first way, as I said in this thing, is you will connect like the 2 pole of this of the first 2 row into the position over here on the circuit kit. We name I think for this demo is 5 volt and ground. GND mean ground.
Sam, doesn't matter which one we're using.
What, like, do you mean row, or do you mean the type of
Color
power?
of the wire.
Yeah, nah, it's fine. Actually, let's give us a quick introduction to the wire. So we have like this type of wire that mean male to female. And like I think we use it to connect to this row over here, because like these are the one that need the female to male wire. And for connecting within the black bar, we will use the male to male wire. That means there's like the 2 things over here sticking out on top. Yeah. So like you will use this thing to connect the component. Actually, this is the very bad one. We use it to connect between column for this row, and between the this row and this row. And don't worry about this wire. This wire I just my specialized wire to do the demo, because if I use the jumper wire, these are called jumper wire, and like they're very flexible for you to move the component around on your breadboard. And yeah, so let's back to this. So like, yeah, we will like, you will use the male to male. I will do it right this side, male to male wire to connect one to connect the ground to the 5V to 5V. And by convention, I just love to connect the positive positive side of the power supply to the red band, and the ground to the blue band. So, and I think the color, I think I messed up the color in the cable over here. Yeah, so we will connect the 5V to the red band over here, to the red row, and the ground to the blue row. Like that is one way to power the circuit. And after that, to supply the power to the circuit, you will turn on the switch over here. That's have the work 5V. And you can also have the option to like do a 3.3V power supply to your circuit. And this one is actually will be used for your up-arm lab section. This one is 12V. And if you did your homework, like the 12V power supply will be used to power your up-arm. And yeah, so like this one is just a hint for your upcoming up-arm lab. I use this to write your lab, I'm still working on that. Any question regarding the first way to power the circuit?
Can you show us the wire again?
The wire? One moment. Let me clear. What do you mean by the wire?
The wire you put in for voltage.
Okay, so like I think like it's in the picture, but I think I can show it to you. 1 second. Back away. Hope you can see it. We have the red to red over here, so it's by the 5V and the ground to the two over here. So that this is the connection. I think my picture when I took it was not really clear. And then to power the supply, just remember to turn on the switch over here to power like the circuit from this thing to this to the circuit.
Okay, thank you.
Yeah, and like, yeah, like for each of the row over here, actually let me use this pen. For each of the row over here, we have 2 row, and you can use either row because they all supply. For example, for the 5V you have 2 slot. You can use either slot. They will like provide the same voltage to the circuit.
So now that we did that, that whole row is powered, or what is powered now that we connected those?
This whole row is power. This
But
whole row
not
now
the
have
row.
the 5V voltage.
Okay. What
And
about
this, like the first whole row is now the ground. Got it? Yeah.
Do we connect the ground to the positive and the volt to the negative?
The volt, like I connect the ground to the negative and the 5V to the positive.
Okay. So the 5 volts to the positive and the ground to the negative.
Yeah, like that's just convention. You don't have to do that. It's just like you can actually switch it and it's give no problem at all. But just remember, for whatever like the convention you choose for crowd, connect it to crowd, like just remember to connect it to use it at crowd and not the other way around, because like otherwise your like for
Okay.
example for the direction no sensitive circuit components such as the diode or the LED, it will either power light up the LED or not, depend on the direction.
Okay.
Yeah. Good.
So if we set, can you show that your breadboard again? How did you connect the? So how did you connect the first two columns with the rest of the board?
Yeah, like that's just convention. You can actually connect these two circuit component, like these two wire, to any of the column along the first two row, and it's work just fine like this, and it's just mean the same thing. You don't have to worry about like where you connect the circuit component, like the wire, to like the first two row, because they are like they are all a single node. But like for this is a convention, so it will be easier for like for us to look at and to know, okay, so this is the power supply, and to trace back the circuit. But like, yeah, got it. Like you can connect like actually
For now, yes.
like
So
you can actually connect this
can we
thing
go for?
and this thing to these two wire, and it just means the exact same thing. There's no problem with that.
Yeah, I did that, but now I don't know what to do next.
What?
Like, are we going for an example right now? Like doing the
Actually,
resistor and the
we are going to an example in about 10 minutes. I just need to cover the two
Okay.
other way to like power the circuit. Like so,
Okay.
because like you guys will need that for like your homework assignment. Yeah, like that will be clear. Actually, if you like if you want, you can just scroll down in your lab manual, and I think there's an example to that. The second way is like the second way to, how do I say it? This what like the first way, when you use it, like when you use the first way to power the circuit, like the graph of it will be actually, I can use it in terms of graph.
I have a question.
Yes.
So can you quickly go over the wire name again, like you showed us?
Oh, okay. So let me show this. So this thing is the female to no, I mean this one is male, because like this has the stick sticking out and there's no stick, so it's the female, and you use the female, like this female, to connect to the hole, like this thing, like this hole on the circuit, like this hole over here. You would use the female to like connect to the pin, the whole pin on top of your wall. Like
And
this.
the one in the previous example, we used the other one, right?
Yeah, we
They are
use the male to we use the male to male, because like like over here we have the hole over here and we have hole over here, so we will use male to male, male to male to connect these two holes together.
Oh, makes sense.
Okay.
Thank you.
And any more question regarding that before we move on to the second part way to, oops, I just erased it. God damn it.
Sam,
Yes.
we got 2 questions in the chat.
Oh, okay. Actually, I don't see. Sorry about that. Let me chat. How do I see the chat? Oh yeah.
I can tell you the questions. One is Is for the homework, is it just for them to fill out the resistor table? And what
Uh,
is the highest resistor value?
The second highest resistor value, read your manual in
Mhm.
for module 1. There's a hint to that. Actually, there's already like the second module is kind of the answer to the first module, but like I just want you guys to have some work to that. So just read the second manual, the second module. Yeah, like I think for the homework, like if you are filling out the resistance value should be simple. And I think that's for the second part. I think I don't know how we are going to create this, but I think like I already wrote the manual for the second part of the lecture, but I don't think I will have enough time to cover it. So you guys will have to try it at home. But like this is the part where I want you to like do for homework, which is like the one we will cover in class will be we just light up the LED and the LED will stay on. But for the homework, like I'm going ahead of myself a little bit, but the second homework, it will be like you will connect you will use the wave generator as a power supply. And by doing that, in conjunction with the software, you will cycle the power supply from 5 volt to either 0 volt or minus 5 volt, and in turn will turn on and off the LED. Like just like this over here, actually, like you will have to read the lab manual for that. So yeah, and I think I will talk to Jacek of how to do it, but maybe film a 10-second video on how to for your result, I guess. Did I answer your question? Let me look at the chat again. Okay, I hope there's no more question. Let me leave it on my second screen. And for the second, I just covered my second, the second way to power the circuit, which is this way. So for the first way, when we connect the power supply to this pin over here, this is the actual graph of the power supply. This is the volt, and this is like over time. And when you connect it to 5 volt, it would just be stable over time. But when you use the second way to connect to power the circuit, you will have another way to choose to like you have the option to choose like how your power supply will look like for the circuit. For example, in the example I just show you guys, you will have the option to use the sinusoidal as like your power supply. That means your voltage will go from 5 volt to minus 5 volt over time, and which in turn your LED light will turn on and off. And we will do that in, and let me do this. Okay, so like I hope you know how to power your board and connect it to your computer. And once you've done that, you will want to turn on the board and open the software. And to do this, come on, computer. I know what's wrong. One moment. And yeah, like when you connect, when you already connect the circuit, like to look like this. Also pay attention to this part over here. It's so moving part. I hate this. Like this one have the positive side and the ground side. Just pay attention to which row you choose at the ground. Just a note. And yeah, And oops, I need to turn this thing off, and there's no hotkey for me to do it. So yeah, when you already connect that thing, that like your circuit as a power supply to like those two pin, and you can use this interface in your software, this option in your software to change how your uh voltage source behave. Yeah, so yeah, it will go like this, and you will have the option to choose the frequency, the period, the amplitude, and for example, in the circuit, we can choose, we can change this thing to 5 volt. And I think for the homework, just about 1 or 2, I mean 1 or 2 hertz should be more than enough. 1 to 5 hertz should be more than enough. Higher than 10-20 hertz is maybe a little bit too high for the camera, for the phone camera to capture. So yeah, just change your frequency because before you actually power your circuit. And this is the offset. Don't worry about this. Phase symmetry, phase. Don't worry about these two things. Phase is just like changing when to start like this. You guys would learn this in Dr. Para class. Any more question? A lot of question, I hope. You don't know what to ask. Nope. Just play with the circuit then. Yeah, this you will like you guys will need this to do your homework assignment. Not homework, but just lab assignment. Nope. And the last thing is this way, and this way I am not a fan because it's kind of complicated, but yeah. So to power the circuit using the third way, one moment, let me check. Oops. Yeah. Oops. To power the circuit the third way, you would like use this thing. You would use this interface to power the third way. And to do it, you will need a special group of female to male jumper cable, which is I am showing on the computer over here. And yeah, like this, like they should have a small bump in the group, and it should be like this is a group of 6, and that should be a small bump on top of it to connect to the group over here, to this group over here. I should change the color to, yeah. And yeah, don't worry about this one. I just leave it there for your introduction, just so you know there's another way to power your circuit. If you want to play with it, you are more than welcome to. Any question? This is the jumper cable. Yeah, by the side, and let's look at this. Nope. We're happy to move on then. And this is the part where you guys have been waiting. This is the LED circuit, and we will go through this, and I hope I can show this. Let me just, yeah, I can move this thing around. That's good. So to power this circuit, somebody left, but that's fine. So to power this circuit, you will use this diagram over here, and I will explain the diagram in the actual circuit picture that I took. Too far. So over here, we have the 5 volt, like this is the voltage source, and this is the positive side of the voltage source. This will go to the resistor. I will call this R, and then go to the LED. And wait, I think I did it the wrong way. I think Like in my circuit, it's the other way around. The LED, this is my circuit. And yeah, and then we have the LED. And then we have the resistor. Yeah, like don't worry about this. This one is the other way around, but like they should mean the same thing. But like this is the actual circuit that corresponds to the graph I make over here. And don't worry about like where you place the resistor before or after the LED. It's like because they're all connected in series, so it just doesn't matter. And to do this circuit diagram over here, I will show you. So this is the 5 volt. And let me do the red color. This is the 5 volt. And 1 second. God damn, I have to draw this again. Let's try this again. I have the LED first, right? And then the resistor, and then to this, and we call this R. So from the circuit, we have the 5 volt, and this one will go into the positive side over here, and then the circuit component will will go to this, and using this jumper cable, it will go to the long side, the long leg of the LED, and then you will connect the other leg of the LED to another column, like over here, maybe. And then from the other column, like in the same column, you will connect one leg of the resistor to it. And then for the other leg of the resistor is in another column. Yeah, like it's not sure because the leg of the LED is a little bit bended, but like it should be in the same column with this wire over here, and this wire over here will connect to the ground, and together this circuit is closed, and you can light up the LED just as over here. Oops. Yeah, the LED circuit is on. Any question?
Could you show your breadboard again?
My purple. Okay. Yeah.
Which resistor are we using?
Oh yeah, that's a really good question. The resistor I'm using has the color, just note it down. And I'm not giving away the value, but just note it down. The one I'm using is brown, black, and I think red. Actually, I just and go. It's 1K ohm resistor.
So let me get this right. So you did one of the LED, the long leg, right?
Yeah,
The
the long leg of
leg.
the LED should like the positive side of the voltage source should come into the long leg of the LED.
Okay, so the voltage source, we did 5 on the positive side. We put the long leg on that line, on that.
Yeah.
And then the other short one on on the other part of the board.
Yeah.
And then on the same column, you did one leg of the resistor.
Yeah.
And the other leg
is in another column.
Is in another column. And in that
column will
you connect it to the ground.
Bingo.
How do you connect to the ground? Do you use a male-to-male connection?
Just use another jumper wire to connect that column to the ground. Like actually you can do something like this.
Because I see you have
I use a special jumper wire just so the picture is clean to be in the lab manual, but you can use a jumper wire to connect it to the ground like this. Like it's in the green jumper wire over here. I hope you can see it, the green color. And like this is another leg of the LED, and yeah, it's a little bit difficult to see, but this is another leg of the LED, and you will connect it to the ground using the jumper wire. Hope this help. Good.
Can you show one more time, Sam? Sorry, I was trying to see if I could.
That's fine. Don't worry about it. Yeah. So let me explain this circuits again. Let me remove the one moment.
And does it matter if we connected the resistor to the power first and then the LED?
Yeah. No, it doesn't matter. So
Okay.
like this one, I just did the opposite way of the diagram. I included in your lab manual, but like you can like put the LED and the circuit like in whatever order that you want to. You can also like add the two resistors together, and like you will see that like with the higher value of the resistance in the resistor, your LED light will start to dim. Like it will be dimmer than the like if you are using the low resistance value resistor. But like remember to use to connect your LED with a resistor, otherwise you will fry your LED circuits. Just yeah, I think it's not necessary because I think the picture is pretty clear. You don't have to use the jumper wire because I tried to take the picture. I tried that and like it looked really messy on the photo. That's why like I use like the special jumper wire, but like the wire I use in the image should like mean the same thing if you are using the wire in your kit. Just try it and like and let me know if you can light up the LED and we can wait for. Okay.
What happens if we increase the voltage?
Don't include that we actually let's try it. Actually, I'm not increasing the voltage. I am going to decrease the voltage to 3.3 volt and see what happens. Just before that, let me show the circuits again, and I will explain the processing of this circuits one more time. So we have the LED over here, right? And with the 5 volt side of your voltage source, it will come to the red line, and the red line is connect in it share the same node with this wire over here, the jumper wire. Oh, this is difficult to see, this jumper wire. And then it will connect to the LED, and the LED in another node is, let me turn off this so it's clear. Yeah, this is way clear. This is difficult. Yeah, and you will connect this wire to one leg of the LED, and the other leg of the LED is somewhere on this side, and it is connect in the same column with the resistor. Let me wobbling around. Yeah, that's right. Okay, and then the other leg of the resistor is somewhere over here, and it will share the connection, and this will go back to the ground. Like remember, this thing I connected, the whole row is connected over here. I mean the whole column is connected over here, and the whole row is connected over like this. I hope this helps. Is it clear?
Yeah, it's clear. It worked for me for the 5 volts. When I did the 3.3 volts, it didn't light up at all.
Oh, okay. So that means the value, the resistance
High.
yeah, the resistance value is too high. So I think that's the smallest value we have in your circuit kit. So yeah, that means it cannot be light up using the 3.3 volt, I guess. Good. So it's light up for you, right?
Yes.
Yay, bingo. Okay. So for the homework, like I think I can show you the homework, but just do it and show us your results. Let me look for the special jumper wire. I don't know where that's it. Come on. Oh yeah, I just throw it away right there. Okay, so for the homework, I think I already explained that in the lab manual, but let me do it again. Let me clear. I'm just confused how we connect the resistor with the LED. Okay, so like you don't have to worry about like what the order of the LED to the resistor, as long as like they should share at like only one column. So over here, I think, yeah, I think this one, like this direction can be used. Yep. Like this one, like the whole column over here are connected. So like you can just put one LED into like one hole in that column and another LED into another hole of the same column, and that will be connected. And then the other leg of the resistor can go to another column, and like from a different hole in that column connect to the ground using the 8-jumper wire.
Sam,
Yes.
the jumper wires are just the male-to-male connections?
Yeah. Like to connect the 2 hole, you will need to use the male-to-male jumper wire.
It's not working for me, and I kind of set it up the same way that you did in your thing.
Did you turn on the power supply?
Yeah.
If you want to show me your screen or your camera, I can take a look if you want.
Just 1 second.
Okay.
You see?
Okay, yeah, I can see it. Let me do this.
How I set it up, and I don't know that.
One moment. Spotlight, I will show you as.
Oh, you didn't turn on the power. See, is it plugged in as well? Yep, power's in. Okay. Can I see the actual circuit?
Can you see it? Let me know if it's
Yeah, I can see. What? Oh, too far. I don't. Sam?
I cannot see it. One moment. Like, don't worry, it's not your fault. Let me try to make this bigger. It's
Okay.
Did you take off the piece of foam at the bottom of the circuit board?
Yeah.
Okay, 1 second.
Do you have your capacitor connected to the same for the LED, I think?
Like how about the polarized, like the long leg and the short leg?
Yeah,
You
I have the
check that
long
as
leg
well?
to the positive and the short to the negative.
That is strange. 1 moment.
Did you use the correct resistor?
Yep, brown, black, red, yellow.
Black, red, yellow. Okay, that is strange.
And I changed the resistor and the LED, and it was neither of those.
How do I see it? Let me stop sharing screen so I can see. Oh, I can see. Like, just move it up a little bit, and let me see. Okay, you use the other 2 ground and LED go up and jump a wire. Okay, that doesn't look anything wrong to me. Just 1 moment, let me see. Yeah, I don't know what's wrong. Did you try the another LED?
Yeah,
Let's
I used to, and it was not.
Strange.
Are you sure that the ground is what you're assuming?
Yeah, it's all
the
connected.
ground?
I just push the jumper wire like really hard down. Maybe your jumper wire is not properly connected to the breadboard. Like also
Even
the
the
resistor,
resistors
the resistor as well.
Yeah,
Like
and the LED. Make sure they really
No.
like push to the end.
yeah, they're all the way in. It's just not working.
that is strange. Yeah, like it's really difficult to diagnose over
I know.
the video. The 5-0, and yeah, it's on for me. The circuit is on the 5-0. Can you show me your circuits again? Okay.
Yeah.
Move it a little bit. I just want to check the color. Yeah, your 5-0 LED light is not on. Like if you look at the side over here, like you will see if you turn it on, like the power supply will on. Like there's a switch over here as well. So just like you can you see it?
I see that it's not turning on for me. Which switch did you press?
Like the 5-0.
Yeah, my 5-volt was on, and it's.
But like the light, the LED light.
The side switch. There's a switch on the side.
What switch? I mean, the full power one is on.
Yeah, the full power one is on. So, but like for some reason, your 5-volt LED is not on. I don't know why. Like your 5-volt LED on the side is not on, right?
Yeah, like it's not showing that I have 5 volts of it powered in.
That is strange. Are you sure that you remove the paddles, like the thing underneath the circuit?
No, under the white.
Right, this thing. You have to remove the entire thing.
Okay, that's probably it then.
Okay, now that's the problem. Oh, like it's really easy to remove.
Magnetic.
It's magnetic.
On the black.
On the board itself, is there a sponge?
Yeah, got it.
Yeah, that's it. I'm just insulating. It's gonna work now.
Well, my light's turning on, but there's still no. All right, yep, it works now. Thank you.
Yeah. Okay. Anybody else have any trouble with your circuit board? Just shout out and we will help you to figure it out. Nope.
Sam, how are we supposed to submit like the homework, the lab assignments?
For the lab assignment, that's a really good question. I will try to answer to you guys by Wednesday. We still haven't talked to the Dr. Domochowski about how you will submit it. But I think the idea is we will like for this one, I think you can just download the PDF or either download the PDF or make another copy to your own personal Google Drive and fill in the table and then just download it as a PDF and submit it. And for the circuit, just take the picture of your circuit of the first one, of this one. And for the second one should be a video for up like a short video about 5 to 10 seconds of your LED light blinking at whatever frequency that you choose, because like even though if you choose a really high frequency, when you try to film it using the video, it should kind of blinking, but just make sure that you can see it's blinking, actual blinking on your screen. Got it?
Okay, so we still can't submit it yet, right? It just once you...
I think we will have to flash it out with Dr. Domochowski.
Okay.
And and now you can try to do it using the second way to power the circuit, which is using the waveform generator. So just do everything the same thing except for the power supply. This time connect it to this plug over here, just like show you, just as in the manual, which is let me share my screens again. Share screen, desktop one. Yeah. And like actually I shouldn't share my screen, but yeah, if you can see it, like it's kind of like the jumper wire, like there's like a couple, like two jumper wire in couple, like they are kind of like together, and like this male to female, and you will insert the female side to this hole over here to use as the waveform generator. And just pay attention to like which color is the ground, and then connect it the same thing to your breadboard as your as the first way, as the current one, and then use the waveform generator to play the circuit.
Are you
Actually, let
looking
me
for
do
us
this.
to do both of them for the lab, the one without the waveform generator and with it?
Yeah.
Okay.
And just try to do it, and it should be exactly the same thing, but like you will see the LED light blinking. I will do it for you now on your video. Yeah, let me try. Supply wave generator, and let me do it as 2 hertz, 5 volt. Yeah, you can choose what light, if you can see the LED light blinking. And actually, I think you're seeing my screen, so you saw what I just did, and now the LED light blinking. And just record 10-second video or 5-second video of this along with, like, yeah, and you should be good to go. I'm not sure if I cover the other thing, the other segment that I wanted to do in your oscilloscope. Any more questions? Oh yeah, I forgot. I knew it. And to take it, I think for this one, you also need to do one extra thing, which is using the oscilloscope to observe the behavior of your circuit. And to do this, you will, one moment. Use another use another pair of the jumper wire, connect it to the oscilloscope, and connect it in parallel. You will have to figure it out. Actually, I will show you, but I will not explain it, and you will have to do it yourself. But connect it to in parallel with your LED, and then use the oscilloscope to observe the behavior of the circuit. So you will connect your circuit to like this, which is, I will show you, like the pair of jumper wire, female to male. The female side will go to the oscilloscope, and the male side will connect in parallel with the LED. After this, I think I already show in the image. Yeah, actually in the image I show like one side to the LED and the entire side to the circuit. Let's do it that way in parallel. So this means what we are doing is the actual circuits will look like this, and this is how we will use this thing as a voltmeter. Supply, and yeah, let's try this. Hang on, my tablet just died. Okay, it's not working again. So this is the actual circuit. Yeah, it's a bad drawing.
I'm confused. So you used both.
Hang on 1 second. So this is the actual circuit that I am showing on the screen. And what's your questions again? Sorry.
I'm confused. So the third way. So the second way I understand, but the third way I don't understand.
The third way, the third way to power the circuit.
Yeah, the one you're explaining right now.
No. This one is not the third way to power the circuit. This one is we are using the oscilloscope as a voltmeter to observe the behavior of the power supply.
Oh, so the oscilloscope is basically a voltmeter.
Yes. And we will observe the behavior of the circuit up the like because we are using the waveform generator as a like to cycle the voltage supply in the circuit. So if we are using like if everything works at exactly as we are expected, then if we look at the voltmeter, the behavior of the voltage in using the voltmeter, and in this case oscilloscope, and look at like the voltage in the circuit, then it should have the sine wave of it. And like this is exactly what the circuit is showing. Oops. Yeah, we have like we connect the part the waveform generator to 1 second. We connect the ones like the waveform generator to this part, use it as a power supply. The same thing as the circuit that we work on, but like the extra thing is these two things along with the 2 pin from the oscilloscope will be connected to like across the circuit. I think actually no. I am bad. I need to be corrected. We are measuring the voltage across the resistor. This has been a week since I look at my work, so I don't remember anything at all. So this is the actual supply circuit of this thing. It's a little bit messy, but you got the idea. So we are looking at the voltage behavior across the resistor. And this is how it should look in your oscilloscope. You will need to master this very well, otherwise you will have a lot of trouble in Dr. Para class. So like when you do that, don't stop the waveform generator, otherwise you will not observe anything in the circuit. And to do this, let's us like look at the scope. And since this one is already running, let me clear out this things, clear my drawing and turn it off and then run. Oops, thing not working as expected. I don't know what happened. Oh yeah, I know why. Oh, so like this thing is like also one of the things like you guys seeing my screen, that right? This is kind of important. Like you will need to adjust the range like this. I think nope. This one is too. Oh, wait, what? Nope. Oh, hang on. Oh yeah, now I see. Nope. Oh yes, up a little bit. Bingo. Yay. See? Yeah, you will need to adjust the base a little bit and as well as the range to show the oscilloscope. But this one show like the waveform generator is working as we expected. The voltage is cycle from 5 volt to -5 volt. And I think you would need to take a picture of this one to be in your lab report as well.
Quick question. So for my scope, it goes up to like I put 2 at 5 volts, and then it goes to 0. It doesn't go to -5.
You will need to adjust like is the waveform generator, the amplitude at 5 volts.
Yes.
Man, that's strange. And maybe you need to adjust like if you like adjust the base, like the frequency based on your frequency, you need to adjust the time base and as well as the range of it. Just play around with it. It should show the same thing.
Because it shows what you have in the lab manual, but not what you have now.
Oh, okay. Maybe because my connection is different.
So it has that where it goes up and then flat lines at 0.
Oh, okay. Yeah, my connection is bad. My connection is bad. One moment, folks. Sorry. Yeah, it's the other way around. Hang on.
Okay.
Yeah, it's the same thing. Yay, bingo. Yeah, like before I were across the entire circuit. That's why it's from 5 volt to minus 5 volt. But now it's across the resistor and like it's behaved like this. Good.
Yeah. Okay.
Okay, right? Yay. Oh, we are over time. Any more questions?
Sam, yes. There's something weird.
Everything is
I think it's my connection. Yes, everything is weird. That's true. Do you turn on number? There's not.
No, you don't have to turn on the 5 volt. Like because there is nothing in your circuit connect to the 5 volt 5 volt source.
I have to run both of them at the same time, right?
Which?
The wave.
Yeah, the waveform generator and the oscilloscope.
So
If
the wave, I should do the period like 500 milliseconds, or should I do it?
Yeah, 500 milliseconds should fine. Just play around with it as long as you show us some picture. If it's work, it's just work. Yeah.
But something like it's okay. I think I have it connected. The oscilloscope, I have it connected wrong. I think because it's showing me like the yellow line is going up and down. That's it.
Up and down. Yeah, I think it's fine. Is it fine? And do you want to show me the picture?
Yeah, I can
Yeah,
show
your
my
screen. You can show your screen, and I think we can take a look at how to diagnose your problem.
Can you allow me to show my screen?
Okay, there's no request, so I don't know how to, like, I think you need to request that.
Okay, 1 second. No.
It's not showing anything. Actually, let me stop sharing and you should be able to do it.
Oh yeah. So
yeah, I think you will need to adjust the base time as well as the range. Let's see if it works because it's look correct to us, but like the range,
my wave, that's my settings for the wavegun.
Yeah, and then go to the oscilloscope. And yeah, I think you will need to adjust the range of the first channel as well as the time base. Try a different value. And maybe the range, I guess. The range in the time in the first unit. No. That's one is for channel 2. You don't have to adjust because like we don't connect to anything in channel 2.
Oh, okay. So it's only channel 1. So the offset.
Okay. No. Up above. One moment.
The position.
Yeah. The base. Yes. This one is too high. Yeah, like kind of just play around with it. I guess.
So I play around until I get it right.
Yeah, I hope.
Okay.
Yeah, it's like there's a periodic behavior to the value. So you will need to a combination of the base and the range of it to show the correct image. But yeah, if you play, yeah, it's kind of, yeah, you can see it. Maybe the range is a little bit too high. So
The range is a little bit too high. I said it as 200 as you said it.
Well, what's the value that I said? That I
Oh.
don't remember. Okay. That look like noise to me. Maybe try millisecond. The homework, this homework, I don't know, into like we will let you know on Wednesday. Try the time base in millisecond. That look like noise to us. I don't know. Let me try to remove request control. And okay. Click to start. Let me try this. Oops. Just a little bit.
I have my lamp turning on and off.
Yeah, one moment.
Yeah.
10, 15 milliseconds. And 500-meter division. Let's try. Yeah, see, it's work. Oops. Oh, wait, what?
I think because you scrolled or something like that. So
yeah, see.
So what's the range and what's the base like?
I think the range is it's one per division over here. Like one small division. Do you see the small scale we are seeing here? So it will adjust like the range, and the time is like what the time scale along this axis over here. If you're putting it too small in the nanosecond like you just did before, it will just show like the tiny fluctuation in the voltage.
Okay.
Yeah, like you will learn about this in the para class, but like for now, just play around with this value.
And can you like which parts are the homework? Is it experiment 1, 2, and 3 and 4?
Yeah, like you need to fill out a resistor table as well as like take one picture for like the stable LED circuit and like one video as well as like your image of this oscilloscope for the blinking one. Sorry.
Okay.
Yeah, like I think we will send out another email by Wednesday to like flesh out all the detail.
Okay. Can I get mine?
And that's it. Any more question? Anybody else? Just shout out. Don't worry. I'm not buying. I don't buy.
There's a couple questions in the chat.
Oh, yeah, the homework is up to module 0. I think module 1 will be next week, so don't worry about that. But just take a look before class.
Sam, the
yeah.
person asked if the lab is due next week.
I don't
but
know. I don't know. Like
I think from the conversation we had with the professor earlier in the semester was that labs would be due at the last day of classes.
Okay,
so everyone,
that's better for us.
yeah, it's just so that everyone has time to actually work on the circuit and is not bogged down by it.
Okay, yeah, actually that makes sense because like the first module is just the introduction. The next module you guys will have a lot of fun with that because it will be excruciating. Yeah, you have to test, like you have to work with every different combination of the resistor, like to get the value of that. So yeah, it will be fun. So you will need a lot of time for this homework. Yeah, we will try to send out an email by Wednesday. If any of us forget it, forget about the email, just let us know and we will try to send it as soon as possible. Good.
Thank you.
You're very welcome. Oh boy, my computer freeze. No more question. Bye bye. I almost forgot. I have office hour tomorrow. Thank you very much for reminding me. I will remind me tomorrow.
Oh yeah,
I
Sam,
will
there
have office hour.
you weren't here during that time, but the homework for got extended to Wednesday.
Oh boy, I will have to do this again. Come on. Okay, fine. Good. Oh boy, I will have to do this again. I still have lots of cold, right? Good. No more question. Yeah, you're welcome.
Sam.
Yeah.
The professor's already up to 100 edits in the thesis.
100 what?
100 edits in the thesis.
That sounds like it's lots of fun for you.
He's only on page 20.
Oh, that's why Dr. Cardozo don't want to do a thesis with me. That's why I report to him.
I have a long night.
Oh yeah, I think we will have to grade a midterm as well, because most of the people receive 0. I think Dr. Domochowski.
I think he prematurely submitted the grades.
Yeah. Can you write an email and let them know about that?
We can still. I think we can. He knows. I think we can still go back and update the grades though.
Yeah, I know, but like many people are freaking out because of that. So I think we need to send an email to let them know that like it will be updated because we haven't graded the exam yet. Yeah, can you send an email, please? Thank you very much.
Okay.
Oh.
Sam, you have power over the meeting. You can end it.
Huh? Wait, what?
You can end the meeting now.
Oh, okay. Yeah, nah, just let them know to leave. Okay, that's good. Bye.